to start. Okay, there's a question about the homework. Is there, Carl? You want to talk about boundary conditions?
Yeah.
Okay, what's your question?
Could you just do another example on how we get from what the picture is, what boundary conditions
Right.
to how we apply them?
Okay, I can talk a little bit about boundary conditions. I think in the book there's a table of boundary conditions, right?
Yeah.
So our favorite boundary condition, of course, is the no-slip boundary condition. Which is anywhere there's a non-moving, anywhere there's a wall. So for instance, flow down an inclined plane, for instance, there's a no-slip boundary condition at the wall. Flow through some sort of a tortuous path. Would still also have no slip at the wall. Even if the wall is moving, you would still have no slip at the wall. And so that just means that the fluid's in contact with the wall, and the fluid's going at the same speed as the wall. So no slip is very, very common. Another one is symmetry. Does not always exist. There's no symmetry boundary condition here. There's no symmetry boundary condition here. But this one, it looks like it would be symmetric along the center line, right? So obviously if we had a crazy flow that was, say, like this, again, there would still be no slip at the wall. And also, there would be no symmetry boundary condition either. So this one would be another case where there's no symmetry. So if there is a plane or a line of symmetry in the flow, the symmetry boundary condition says that the flow on either side of the plane or around a line of symmetry must be the same. And so that typically means that there's a maximum in the velocity at the center. So that's typically some velocity component goes to 0 at the line or plane of symmetry. And the third most common boundary condition is stress or velocity matching between two fluids. And on this sheet of paper, there's only one time that's happening, and that's right here. If this is air, the stress is about 0 in air compared to the stress in the fluid. And so at this boundary, the stress is the same as in the air, which is 0. So this is a type 3 boundary condition. One problem that maybe some people in my fluids class saw in a bonus problem was you could have 2 layers of fluid. Say you have a red layer and a green layer. That might be a lubricant at the surface, and the rest of the fluid is green. Then if you move, you could either impose a pressure. If you imposed a pressure, that would be interesting. You might get a velocity field that would do something like that. The boundary conditions on the sides would be no slip. And at this boundary, between the two fluids, the stress and the velocity would have to match. So what I asked for in the homework was for you to put these kind of boundary conditions into mathematical form. So that would be, for instance, let's see. I'm trying to pick one that's not actually on the homework, but I think I may have one already on the homework. This one I think is there. I won't get the coordinate system correct because I don't remember what it is, but let's say I pick this coordinate system, x, y, and this height is b. Then the two boundaries are the top and the bottom. So I would say for all values of x, when y is 0, the velocity in the x direction is 0. For all values of x, when y is b, that means when y is equal to the top plate, the velocity in the x direction is 0. Two no-slip boundary conditions. I had some examples in the homework where the boundary conditions changed. So there was for z less than 0 and for z greater than 0. For z less than 0, the no-slip was at r, and or r1 maybe. And up here, the no-slip was at r2. So it's just a matter of writing those in terms of the variables of the problem. What else can I tell you? Did I answer your question? Okay. Any other questions about the homework? Anybody want more time? I can give more time if you need it. So the homework's due today. The main office closes at 5. Otherwise, you can slip it under the door of my office up till midnight, I guess. That would be okay. Or if you want, you can send me an email and tell me how much extra time you want. And I'm open to that. I'm actually going out of town, so it doesn't affect me at all if you want to take a little more time. But I've only talked to 2 people about questions on the homework. I wonder if there are others who have questions. If you do, just send me an email. I should be in email contact this weekend. Yeah, David.
For your boundary conditions for all x, y equals b,
yeah.
Wouldn't your bx equal like b max rather than 0 there?
Oh, you're right. I did it wrong. Good point. This one is the stress is 0. This one. The stress at that location is 0. Thank you. What was I doing? I was doing the 2 plates. If this is air, then this should be that the stress is 0. The stress on a y surface in the x direction is 0. Thank you. This is the same as dvx dy equals 0 because of Newton's law of viscosity. Tau yx equals minus mu dvx dy. And so if this is 0, then this must be 0. So this is the same as what you said. The velocity is a maximum. I was going too fast. Thanks for catching that. Actually, we haven't gotten up to Newton's law of viscosity. That's where we're heading today. So this draws back on your previous fluid mechanics experience, but we haven't talked about that yet. Any other homework questions? Okay. So let's try to plow through to the end of the Navier-Stokes equations today. So let's review what we've been doing and where we're going. Let's see if this is working. Looks like it's working. Yes. Okay. All right. So going way back to the beginning of our Chapter 3 discussion, we're just trying to derive the microscopic momentum balance. So this is the microscopic momentum balance. The rate of increase equals the net flux in plus the sum of the forces, otherwise known as F equals ma. But this extra term comes about because we're doing a control volume balance and not a body balance. So this is a result of our point of view. So this is our volume, and it's enclosed by a surface S. It's a volume V. I haven't said what its shape is so that everything we derive is good for any shape. Each little piece of volume is just located somewhere inside. Each little piece of surface is located somewhere on the surface and has an associated outwardly pointing unit normal that tells us what is the orientation of the surface. Because at a given point, there's no telling what surface we might be talking about. We're talking about the surface piece of surface that encloses V. So that particular piece of surface is identified by saying what its unit normal is. And in this sketch, the vector B is just some property that we might be interested in. And in our case, that might be the momentum, because we're doing the momentum balance. So we have these terms. The rate of increase terms comes from writing the mass in the total volume and then taking the time derivative. The net flux in term comes from writing the volumetric flow rate in, which is n dot v VDS, that's the volumetric flow, and then multiplying by the momentum, rho v, and this dyadic tensor showed up. So that's the net flux into the volume, and the minus sign comes because the n was the outwardly pointing unit normal, and to make out in, you multiply by minus 1. And the body force terms were F equals ma. Mass times volume is mass per volume times volume is mass times acceleration is ma. Integrate over the total volume gives the total force. And then we spent last time on the stress tensor. And the point of the stress tensor, my idea for how to teach this is we've gone through it once, and now I'm reviewing it with some familiarity. You've seen it, you know where I'm heading, but maybe the words will mean something different the second time through because you know that at the end of this discussion, the stress tensor is appearing. So let's see what that stress tensor, what I said it was due to. Maybe now this will be another pass. We can pick up a little bit more. We're examining some point in a fluid, and we're looking for an expression for the stress at that point. That point might be in the middle of the fluid. It might be at the wall of a flow. And the idea is we don't really want to say. We just want to know some mathematical way of saying what the stress is at that point. And then later, we might say what surface we're talking about. So these stresses we're talking about come from molecules. And we're taking the point of view that we don't want to talk about no molecules. Okay? We just want to talk about math. Now, that might be not your point of view. You'd rather talk about molecules. Chemical engineers usually start with molecules. And that's a very reasonable point of view. This is just a little side path into getting the math that will be very handy. The math will be the vocabulary that we use to store this information about molecules. We'll eventually have to come back to these molecules. But at the end of the day, we're going to give our answer in terms of this stress tensor because it's a very handy mathematical way of representing a very complex behavior, three-dimensional behavior. And so we're going to talk about the stress tensor first, and then we'll talk about molecules. So the stress tensor comes from a consideration of stress at a point. So there's some point here. This is some arbitrary surface through that point. I orient the surface by declaring what its unit normal is. And this is the force on that surface. Force per area is the stress at P on a chosen surface. We define the components of the stress tensor as the components that tell at that point P what the stress would be on three chosen surfaces that are the ones that are perpendicular to our coordinate directions. So we're just using this for nomenclature. And we use that nomenclature to define the vector forces on those three surfaces. But at the end of the day, all we get out of the stress tensor discussion are these stress components, that there are such stress components, the stress on a P surface in the K direction. And the next part of the derivation is where we relate that to an arbitrary surface. So we have these 9 stress components that relate to the stresses on these 3 idealized surfaces. Then what we do is we say, okay, take an arbitrary surface. It has some force on it. That force, it has a contribution from forces in the 1 direction on a 1 surface, forces on a 2 surface, and forces on a 3 surface. And that's how we relate the forces on these idealized surfaces to the general forces on a surface. So here it is. This is how we did it. We picked an arbitrary point. We picked an arbitrary surface. This is the force on that surface in our fluid. It's a vector. Without knowing anything about it, we can write it in our coordinate system as F1E1, F2E2, F3E3. In words, F1 is the component of the force in the 1 direction. F2 is the component of the force in the 2 direction. And F3 is the component of the force in the 3 direction. And we pick, for instance, F1 and know that it must be some combination of the force on a 1 surface in the 1 direction, on the 2 surface in the 1 direction, and on a 3 surface in the 1 direction. Then we had to figure out which part of how to combine these 3 stress components. And the answer is they combine by the projection of our arbitrary surface in those 3 coordinate directions. Okay? And so pi 1, 1 is the stress on a 1 surface in the 1 direction. So the projection of S, shine a light in this direction, get this shape. That proportion times that stress gives the contribution from that stress. Shine a light in the 2 direction, get, or let's say down, in the -2 direction, get this shadow, that projection. That proportion of area times the stress on a 2 surface in the 1 direction gives that contribution. Shine a light in the -3 direction, get this proportion, this amount of surface area, and that gives the contribution of the force on a 3 surface, because this is in some sense the fraction of our surface that is got a character of a 3 surface. When we add those all up is when the stress tensor appears. And this now just becomes tensor algebra. These are those 3 projections multiplied by those 3 components. We factor out the n, we factor out the ds. We combine, we write this f, this was just for F1. We write similar terms for F2 and F3. We put them all back into our original general equation for F and work on the algebra, again factoring out the ds and the n dot. Lots of algebra later, we end up with n dot, pi ij ei ej. That's what this is. Pi ij ei ej, where I and j go from 1 to 3. So there it is, pi pm ep em. And so that's this final and then result. This is a beautiful, simple, handy final result. Okay? This final result is a very simple way of saying what is the force on a surface if I know the area and I know the orientation of the surface and I know this machine, this stress machine that can tell us what the final force is. N dot the stress tensor multiplied by the area gives the force. No matter what area I pick, I just have to put area in, put its orientation. This machine tells me what the force is. So if everything I did up to now made no sense whatsoever, you can still get value out of the lecture by looking and thinking about this equation. This is the state of stress at a point. because I can tell you, it's like a magic trick, you know? Give me any surface at any orientation and I'll tell you what the force is on that surface. And now we have to talk about what this thing is. So first we'll put it back into the Navier-Stokes equation. Here's our momentum balance. It's all new stuff now, no more review. Rate of increase equals net flux in plus sum of the forces. These are the terms we've done already. This is the missing term, which we can now do. The molecular forces are the sum of molecular forces on our surface. N dot pi is the force on a surface. We can then integrate it over the whole area, and we get this final term. And then you can use the Gauss divergence theorem to turn that into a volume integral. Now I've hedged one point, which is this minus sign. And this minus sign is related to the sign convention on pressures. So Carl, you're a mechanical engineer. We use an opposite convention to what you're used to. Tension is positive for mechanical engineers. Compression is positive for chemical engineers. So there's a sign convention difference, and that's this minus sign right here. Compression is positive, and so this becomes a minus sign here. It's really not that serious. I'll point out where those minuses are. It'll only bother us when an actual pi appears or later a tau. If it's just got v's in it, the signs are already taken care of. If it's got velocities in it, we're good. But there will be a difference when I say, what is the stress? But I'm not planning on docking a lot of points for that, but there is a difference there. Okay, so let me go back to slow mode here so that you can see the final steps that bring us the Navier-Stokes equation. This is what we have so far. This is a microscopic momentum balance. We have this rate of change term, partial with respect to t of rho v dv. That was the rate of change of momentum in our volume. The net flow in after the use of the Gauss divergence theorem was del dot rho vv dv. The force due to gravity was the integral of rho g dv. And then the molecular force term after the inclusion of the Gauss divergence theorem is a volume integral also, del dot pi dv. Okay, so we have a left-hand side and a right-hand side. This is the rate of change of momentum. The net increase in momentum equals the net flux in plus the sum of the forces. Now, they're all volume integrals, so we can all move them to one side and put them under the same integral sign. Partial with respect to t of rho v plus del dot rho vv plus del dot pi minus rho g dv equals 0. Now this is the same point that we made in the mass balance. We're taking an integral over a fixed volume v, but it's a fixed arbitrary volume. Arbitrary means we can pick any volume we like. Any volume, big, small, any size, any shape. We can apparently integrate this combination of things over any volume, any shape, any size, and we will always get 0. There's only one function in the world that you can integrate over any possible limits and always get 0, and that's the 0 function. So that must mean that what's between the square brackets itself must be 0. So we can drop the integral signs. And we get partial rho v with respect to t plus del dot rho v plus del dot pi minus rho g equals 0. Now, there's two things that are different between this equation and the Navier-Stokes equation. Okay, we'll cheat a little bit and look ahead. What's the Navier-Stokes equations look like? It looks like d rho dt plus v dot del v equals minus grad p plus mu del squared v plus rho g equals 0. So we can just look ahead, kind of like we always do, right? You know, it's always good to look at the answer and work backwards, work forwards a little bit. What's the difference between what we have now and where we're heading? Up here we have rho v together in the derivative, and here we have, excuse me, I did that wrong. It's rho on the outside and v at the top. That's the Navier-Stokes. So it looks like we just pulled rho out and that we're limited to constant density. That's not correct. That's not going to turn out to be needed. But that's what it looks like. I'll agree with you there. V dot del v comes from this term. But this term, you know from the homework, right, is a product rule. So this one, when we do this in Einstein notation, we're going to have to do the first times the derivative of the second times the derivative of the first. And then we're still going to have a product. We'll have to do the first times the derivative of the second times the derivative of the first. There's a lot of stuff going on there. Okay? So this is a lot of terms. This is also a product rule. Rho times the derivative of v, v times the derivative of rho. Also a product rule. It turns out that when you work on these with Einstein notation, that the continuity equation shows up. Okay? Turns out that the continuity equation shows up. And the continuity equation, I don't have it here and I don't have it memorized. The continuity equation is two terms that sum to 0. And so those terms, because of the mass balance, they sum to 0. So I'm not going to waste our time on it, but you are perfectly capable of doing this. Okay? It's not rocket science. It's just taking these two terms and eliminating. There'll be some terms that are the continuity equation. And what's not the continuity equation is this. This becomes this, and the hint is the continuity equation, the mass balance, drops out. Let's see if I can remember it. It's the rate of change of the velocity. I think it's check this. I think that's the continuity equation. Okay, but these two terms are in there, and it drops out. What's left behind is this left-hand side. So I'll leave that to you. I think it's either in the book or, is it correct? Well, good for me. I had no idea. So that drops out of all this mess, which you can sort of see that it's in there somewhere, the first, the derivative of the second. It's in there somewhere. And this is what's left. So the left-hand side, we're actually already there, minus some algebra. What's the deal on the right-hand side? These two terms come from here. And this term is this one. It's just moved to the other side. That's where the sign changed. So now let's deal with this. This is the last step we need to get to the Navier-Stokes equation. So that's what I say in my notes. Here is the version of the microscopic momentum balance that we're at right now. We do not assume constant density, but these first two terms become these two terms. And now we need to talk about the pi tensor. Now, the pi tensor is the, that's that substantial derivative. The substantial derivative is defined as the stuff here in the brackets. We covered that briefly, okay? It's partial of a quantity plus v dot del of the quantity. It's not that important. It's vocabulary. But this is called the substantial derivative, and it's just another way of writing it. This won't be that key to us, but you'll see it written quite a bit in the literature. So let me talk a little bit about the stress tensor. The stress tensor pi, I like to think of it as sort of a closet. What we've done is we've said that at some point in space there are stresses. We have a fluid. It makes sense to us that there are stresses. If the fluid were at rest, we would know what those stresses are. They're just pressure due to gravity, ρgh. We did that in undergrad fluids class. Now, if we allow the fluids to be in motion, crazy motion, swirling motion, whatever, the sliding and relative motion of the fluid is causing different stresses at any given point. What's causing them is the molecules. And unless I'm willing to talk about different molecules, I'm not really going to be able to talk much about those stresses, because if it's water, it's different than if it's air. It's different if it's a polymer. It's different if it's peanut butter. It's different if it's asphalt. All these things give different stresses in the same flow field. Okay? So we've derived this mathematical bucket, this mathematical closet that has that information. And if we knew that pi, then we can pick any surface, and we would know that unit normal of that surface because we've picked it, and we would know the stress at that point. So what we've got to do now is start talking about what that pi is, and that's rheology. That's fluid mechanics and rheology, is figuring out what that stress is. And the first thing we do is try to simplify that stress by peeling off the easiest part. So the easiest contribution to that stress at the point is the pressure. Okay, so that's what I'll talk about first, and then I'll talk about everything else. So we're talking about the molecular contributions to stress at a point. And I'm going to divide it into two types of stress. The two types are the easy one, pressure, and the hard one, everything else. So what is pressure? Pressure is an isotropic stress. Okay? So that's taking one word that we didn't know what it meant and defining it by another word or two words that we don't know what those mean. So not very helpful until we discuss what those things mean. Isotropic stress means a stress that is the same on every surface. So we've been talking about this point P and what stresses there might be, and I said if I put one surface through, I'm going to get one stress vector. If I choose a different surface with its unit normal, I presumably get another stress vector. Actually, there is some contribution to the stress that is independent of which orientation I pick. And that's called the pressure. And that's why when you dealt with pressure in your fluids classes, it seemed so much simpler than stress does. And that's why in chemistry classes, when they said pressure is force per unit area, they didn't have to say it was a tensor. They didn't have to say it was anything complicated. They weren't up here trying desperately to tell you about different forces and different surfaces. They didn't have to, because pressure is isotropic. Once I know the point I'm asking for, if I put my pressure transducer up to that point, it doesn't matter what orientation of that pressure transducer I use, I will get the same value. That's pressure. That's not stress in a moving fluid, however. Okay. Stress in a moving fluid is not isotropic, but stress in a stationary fluid is isotropic. So when you did physics and you talked about pressure in a bomb, or in chemistry, ideal gas law, what's the pressure in some vessel? None of this complicated stuff came up because you were only dealing with a non-moving fluid. And the only variations in pressure in a non-moving fluid, rho GH, hydrostatic variations. There are no variations at some elevation. You can put your measuring device at any angle, you get the same answer. Okay. Once things start moving, it's a whole different ballgame. So even when things are moving, though, there are isotropic contributions. And so we typically separate out the isotropic contributions. All right? So we want to separate out the isotropic contributions. And this is how we do it. The stress tensor is equal to isotropic plus not isotropic. Makes sense. Okay? The isotropic part is P times the identity tensor. I'll prove it to you. And the stuff that's not isotropic, everything else. This is called the extra stress tensor, which sounds almost like everything else. And that's really what it is. It's the stress that's not isotropic. Why can pressure be written like this? I said that isotropic meant that no matter what surface I pick, I'll get the same stress. Okay? Watch this. This is actually really neat. Okay? The force on any surface is n dot the stress tensor. We just derived that. So n is how n dot the stress tensor ds. N is how we pick the orientation of the surface. So I'm saying that no matter what n I get, I'll get the same force out if all that's present is pressure. So that means if all that's present is pressure, then I put n dot pi. I should get the same value out and the same direction. So I missed one other thing. Isotropic is same on every surface and perpendicular to the surface. That's what I'm going to get here. I'm going to get a vector that's perpendicular to the surface, meaning parallel to n, and independent of what n is. I'm not going to have to say what n is to get the result. And I can do this in Einstein notation. This dot product is np, oh, p is a bad choice, niei pressure. Now the identity tensor is E with the same subscript in both places, so kk. And there's a dot. So it's EI dot EK, delta IK, and I get N, I becomes K. There's a P, and there's an EK, and there's a DS. Now going back to Gibbs notation, NK, EK is just N. So I get P, N, ds. So the force on any surface, if the only contribution is this, pi, the force on any surface is normal to the surface and has a magnitude of p. So this is correct. This mathematics has this language in it. It produces a stress that's always normal to the surface and is independent of the orientation of the surface. I didn't even have to say what n was. I didn't have to say it was up, sideways, back, and down. No matter what it is, this stress tensor, pi, produces a force that's perpendicular to the surface and of magnitude p. So that's what I have here in the summary notes. Pressure is an isotropic force per unit area. It's due to molecules. It's the same on any surface drawn through a point and always acts normally, perpendicularly to the chosen surface. That is written mathematically as this stress tensor, the scalar P, scalar pressure P, which is the magnitude of that tensor, times the identity tensor, which looks like this. An isotropic tensor has only diagonal elements, and they're all the same. And this is what I just did. What is the force on a surface with n? So now the remaining stresses are called the extra stresses, and they're just P subtracted from the stress tensor pi. So this is the closet that has all the secrets of molecules in it and is the main difficulty from here on out. All right, so this is our final question. What to do with the stress tensor, and that's what we're going to study in this class. If I go back to our derivation of the Navier-Stokes equations, to get from here to here, all right, I can now say that pi is pressure. Let's see, go back one slide. Pi is pressure plus extra stress. So I can work on this a little bit. I'll keep the stuff that goes on the left-hand side on the left. And I'll put the stuff that goes on the right on the right. Del dot pi plus tau plus rho g. You can show that del dot pi, okay, now I'm just distributing these guys here. I have a minus sign missing. Minus sign, minus sign. Because this is on the left side, I moved it to the right. You can show that this is equal to grad p. That's, again, just an exercise in Einstein notation. And so we now get minus grad p minus del dot tau plus rho g. And as I said before, if we eliminate the continuity equation, this becomes rho dv dt plus v dot del v. And I'm seeing that I missed a parentheses here also. So now if we compare the Navier-Stokes with where we are, the left-hand sides are the same. The pressure term has appeared in its correct form. Gravity is correct. And we need an expression for tau. And that's where we stand. In Newtonian fluids, there's an expression for tau. And it's on the next slide. It's right here. This is the correct expression for tau. This is Newton's law of viscosity written in tensor form. I'll talk about it a little bit more next time. For non-Newtonian fluids, tau equals something else. Something more complicated? Yes. Because if you're going to describe non-Newtonian fluids, it's got to be more complicated than Newtonian fluids. Okay, so in rheology, our job will be to change this equation so that it correctly matches polymer wacky behavior that we saw in the video. It has to climb up rods. It has to have memory effects switching back and forth. It has to have time-dependent creep behavior that matches what polymers really do. This equation does what Newtonian fluids do. And the Navier-Stokes equation that you're used to is a simplification of this equation stuck into this one, which is called the Cauchy momentum equation. Don't need to know it. Okay, this is the one we're up to. If we take that equation for tau that goes with Newtonian fluids and stick it in here and do all this del stuff that you now know how to do, you will get the Navier-Stokes equations. So the missing piece from here to the end is that tau equals minus mu times del V plus del V transpose. So you can sort of see why I wanted you to be able to do all of that Einstein notation, because now here it is again. We can either sit here and I can do a lot of algebra, a lot of tensor algebra, or you can go home and do it, or I can assign it for homework, or you can believe that there's just algebra between here and there. You'll take my word for it. But you can see that it's really not that hard. It would just be a little bit of an exercise, because all we have to do is del dot minus mu, parentheses, del V plus del V transpose. It's not that hard. Minus mu comes out the front, so that's not a problem. Del distributes, so we have to figure out del dot del V. Well, that's in fact the term that's in the Navier-Stokes equation. And we have to add del dot del V transpose. Turns out that's 0. You know, it's going to turn out to be 0. Check it. It's going to turn out to be 0 for incompressible fluids. For incompressible fluids, del dot V is 0. And when you do this out, a del dot V appears, and so the whole thing goes away. Tricky. So it's the mass balance that makes this term go away, and then we get the Navier-Stokes equations. And as you saw in the homework, and as you saw in undergrad fluids class, this equation can then be used for solving flow problems for Newtonian fluids. This constitutive equation, the Newtonian constitutive equation, is a full tensor equation that relates the motion of the fluid, material parameters, to the stress. In fact, the extra stress, because there's still the pressure part if we want to get to the total stress tensor pi. In undergrad fluids, you dealt with Newton's law of viscosity. This is the 2-1 component of this under the special circumstance of incompressible fluids, straight line flow, and no variation in the 3 direction. You can do that too. You can check that. So this simple scalar version that you learned in your undergrad fluids class is just one of the 9 terms of this full tensor version of the constitutive equation. There's a summary of what I said on my slides. We plug this in there and we get the Navier-Stokes, and there's our final result. Okay, so we made it. It was a little bit arduous, but we made it to the end. We got the Navier-Stokes. So again, if anybody's not handing in their homework today, please tell me now or tell me by email and when you're going to turn it in. And then have a great carnival, and I'll see you on Monday.